Okay, so I think so. Just 15-20 more minutes for explaining the concepts, and then we'll work with a DNLM model, which is the distributed lag. So the concept of distributed lags is when the effect of the exposure is distributed across lags. So if we are looking at yesterday's temperature, yesterday's PM 2.5, there is some effect of that on today's deaths, but there is also some effect of day before yesterday's PM 2.5 on today's deaths. So the effect is distributed across different lag periods. Now, since we constructed the lags, we constructed them as single lags, or we did it average across multiple lags. Now, if you have those single lags, the idea is to, do it in the same model. So, having all of those lags work in the same model. And the issue is collinearity. So, it will lead to highly unstable estimates. So, if you put lag 1, 2, 3, 4, and 5 together in a regression model, that's the unconstrained distributed lag. And what will happen is for each of those lags, you will get an effect estimate, but those will not be consistent. So they will jump around because of the collinearity. So the way out is to do this in a constrained manner. So if you did the unconstrained one, so you can ignore the lines and just focus on the points. So if I did an unconstrained analysis by putting in these lagged models, so this is 0, 1, 2, 3, 4. So if those 5 lags were put into the same model and if you run it, the effect estimate for lag 0 will, let's say it is here, effect estimate for lag 1 is here, lag 2, so it is jumping around because of the issue of collinearity. So how do you get across that is by doing a constrained analysis, so which is a shrinkage based methods. I don't know how many of you have used shrinkage based methods, but that's a way to deal with such. So it's basically regularizing. So regularizing means, so if you see this, it seems like it is trying to overfit, or it is trying to do too much with too little. So a constrained one would impose penalties on these parameters. So remember when we did our least squares, what were we minimizing? Right, this is what we were minimizing, right? So there's a sum and whatever. This is ordinary least squares, so where we are minimizing this, so you have to minimize. So if this is S, so I'm trying to minimize S with respect to betas. This is what we are trying to get. So the beta hat at which this happens is your parameter estimate. This is normal unconstrained linear regression. So what is the meaning of constrained? So if I put this where this lambda is a positive number, now if I try to minimize this with respect to beta, what will happen? So let's first we'll fix the lambda, and then we'll try to minimize this. So the problem comes here, right? So there's a penalty. So what are you doing here? So you are attaching, when will this become big? Lambda is positive. So when will this part become big? When will it become bigger? Like for what values of beta? So that summation is still the same. So yi minus beta xi square but there's a lambda beta square. So when does that become big? Lambda is positive. For what values of beta will it become bigger? You take different values of beta. So if beta is 0, what is the value of that part? 0. So now, when will it become bigger? When beta becomes big in either direction. So what is the meaning of beta becoming big in positive or negative direction? What is beta? Now what is the meaning of beta? It is the coefficient between what? It is the effect of or the association between the exposure and outcome. So by beta becoming big means, so either in the positive or negative direction, what does that mean? It's a strong association, either in the positive or the negative direction. So for the values of beta where it is really strong association, it is trying to impose a penalty. So to minimize this, you are adding a positive term to that. So it is you are punishing it for becoming very strong, right? So the beta at which, if this was not there, then there would be an unconstrained estimate for that. So if I was only minimizing this part, this would have some beta hat, right, at which this is minimized. By putting this, you are imposing a penalty on what is the value of beta. So what will happen is, because of this constrained analysis, you are trying to shrink the betas towards 0. So only the strong betas will stay, the others will be disappearing. So why is that? So for betas which are, the true effect, if the true effects are not very large, so there are multiple exposures here, right? So because you have multiple different, because this is in the case where you have multiple different variables. So collinear variables, or you have 100 different variables or 50 different variables. So each variable would have a coefficient attached to it. The variables which have weak relationships, if you do this, then they will be minimized because they are small, you are trying to push them towards 0. So the effects are no longer that significant. So what will remain? The ones which are really, really strong, they will stay back. So by penalizing, what you are doing is you are restricting yourself to variables that are really important in explaining the variation. So there are different ways to do that. So if you imagine that you had that polynomial kind of structure, so if you have 3, 4, 5 different parameters, because if you have a very wiggly curve, this is defined by, let's say, 10 parameters. So if you have 10 parameters, not every one is important. If you have the 10 parameters as it is, then it's a very wiggly curve. But maybe it's not that important, just like here. So that up and down is probably not true. So you want to impose penalties so that they become simpler, so that they become smoother. So that's why it's a penalized or a shrinkage based method. So you're shrinking estimates towards 0 or to 0. So this setup will never become 0, it will become close to 0. So this is called a ridge regression. So it depends on what you are penalizing on. So there are systems where you can put a penalty on the absolute value. There are things which you can do it with both, so absolute value as well as squares. So things like elastic net or lasso. So those are for variable selections. By shrinking these unimportant variable coefficients towards 0, you are essentially saying that these variables are not important. So that's one way for variable selection, and this is also a way to get penalized or regularized curves. So in the distributed lag model, that's what we are doing. We are putting in correlated variables in the same model. Not all of them are going to have important information. So that's why we will use this shrinkage based method to get a regularized curve. So that is the basic idea of distributed lag models. So using multiple different lags in the same model, but not letting them run unconstrained so that they are too jumpy. To regularize that, you are using a shrinkage based method, which will smooth out the curve. Any questions? Yeah. This is for estimation. I mean, for this, it is an estimation problem. You are still estimating. So beta hat, if you do just this part, you will get a beta hat unconstrained estimate. If you do using this, there's a cross validation involved here as well because of the lambda. But what you get from here is the constrained estimate. So beta hat C. So if you do a ridge regression, you will get a beta hat, which is the constrained version of the normal least squares. That's still an estimate. It is just using this shrinkage to remove the effect of some of the variables. Those are for variable selection. So, right. So, elastic net lasso, the ones where you have these mod values and combination of that, those are for variable selection because then, so the beta square, this one will never, like each coefficient will go towards 0, but they will never become 0. But if you have the absolute value and all, which is elastic net or lasso, they can get these betas to 0. So for the unimportant variables, they will get the betas to 0. So those are not going to be in your model. So that's used for variable selection. All of these are shrinkage based methods. Elastic net, lasso, ridge regression, there are more like weighted quantile sum regressions. All of those are based on the same principle. But when you are using the betas from a ridge regression, you are using them for estimation purposes. For variable selection, you will not use those betas anymore. So you will just select the variables and then run a separate regression to get the actual effect estimate. So I think Ajit will demonstrate the code. So the distributed lag models, they work the same way. So I think you can set up your laptop. So the basic analysis is like this. So you run single lag models, in this case let's say 0 to 5, and then you do the constrained versions. So you put everything together, but you run it using this approach which is shrinkage based. So the same thing can be done. So if you have 5 different lags, you can put all those 5 lags together and you can do a distributed lag model. The other approach, a simpler approach, is to take the average of those 5 lags and use that as one single variable. The interpretation would change because then you are looking at cumulative effects versus the combined effects. Cumulative effect is what is happening over the last 1 week. This one is different. This one is a joint effect kind of thing. So it is also, sometimes you can have a little bit of difficulty in interpreting results.